So thank you, Dave. That meant everyone can see our screen, right?
Yes, well, I can see it.
Okay, thank you. I'm talking now about the physical properties and downhole logging possibilities on mission-specific platforms. And as Dave already said, it's a joint talk. So we are representing the European Petrophysics Consortium, and we are tasked with physical properties and downhole logging within ESO. The consortium is made up of the University of Leicester, which I'm representing today, and Leicester is mainly dealing with the physical properties aspect, and Erwan, who will speak in a couple of minutes, is representing the University of Montpellier, and they're mainly dealing with the downhole logging aspects. Overall, our role is to acquire and interpret downhole logging data on mission-specific platforms, work on the core petrophysics, and deal with the data calibration and quality control. So we make sure that the MSP data is comparable to data that has been collected on the other two platforms and in the past. And we assist and advise IODP proponents, such as yourselves, on the downhole logging and physical properties, data acquisition, and capabilities on mission-specific platforms. And I just want to reiterate what Dave just said. Of course, the science has to come first, but it is always great if you reach out to us and ask us all the questions and concerns you have about physical properties and downhole logging. We are very happy to help you navigate the MSP proposal writing process. And it always comes up during the review process. The Watchdog 5, which is responsible for the operational aspects, is getting asked, well, did the proponents actually talk to you guys? And it's always earning brownie points when I can go and say, yes, they were super responsive. They talked to us a lot. We're really happy with how they're doing. Now I just want to talk a little bit about the physical properties. Physical properties in the IODP world is basically the physical description of the geological strata. So it ranges from density, P-wave velocity, to color reflectance, how much natural gamma ray a rock is giving off, and so on. It's a standardized legacy data set. So at the very beginning of DSDP, similar measurements, for example, for density, have been done. So you can look at the database and actually get density measurements, P-wave measurements from the very first beginning of IODP. And you can always compare those data sets because we make sure that they are all comparable. And during an MSP expedition, the physical properties are the first data set that you actually get along the core. Physical properties are also sticking with you through the whole process. When you start thinking about your proposal, you're looking at seismic methods to figure out where your site actually should be. And that's basically the first time you use physical properties in this whole process. Then when we get offshore, we use downhole logs and look at the core. So we reduce the scale of the physical properties to get a better understanding of your strata. And during the onshore phase, we work on discrete samples to basically narrow down the physical properties even more. During the offshore phase, we mainly work in our containerized lab, which you can see here on the side. We are sailing with a whole round multi-sensor core logger, short MSCL. And during the offshore phase, we collect natural gamma radiation, which already gives you an indication of, for example, the clay content of your strata. We collect P-wave velocity and density data, so you can directly correlate with your pre-site survey seismic data, for example. And we collect resistivity data, so a first look into pore waters or pore fluids, and magnetic susceptibility data, which is a great way to correlate between different coring sites and multiple holes. These are all continuous measurements along the core, and approximately half a day after the core has been put on deck, you get those measurements. As I already said, it's an almost real-time information on your drilled strata. It allows you an on-site direct correlation with your pre-site survey data and helps and guide operational decisions. But it can also provide a lot more. On the side here, you see a figure from a 2016 paper by Morgan et al. On the Chicxulub impact crater. And this high impact paper in Science has been worked on before the cores have even been split, based on the MSCL and the downhole logging data with which they could ground truth their numerical model on the formation of peak rings in large impact craters. So the data is not just a legacy data that you can really work with it from the get-go. Additionally, we can also take more non-standard measurements offshore. For example, if a large part of the core is been dedicated to large samples, for example, for microbiology, we can use an MSCL fast track to get a limited set of physical data from the entire core before the sampling takes place, which has to be done quickly after the core has been on deck. And if we sail on a research vessel, for example, on the Kaimei for the Japan Trench expedition, we can use the hydroacoustic and sediment echo sounder equipment on board to actually use the time between sites, or when the giant piston core has to be reloaded, to actually verify the site survey data and get additional connecting profiles between sites. Dave has already teased a little bit the time between the onshore and the offshore phase. And this is for a good opportunity to do additional measurements on the whole round cores. For example, as you can see here on the slide, you could take CT scans of your whole cores to get a bit better 3D image of the core internally before it gets split and potentially you disturb certain features. It is also a good time to take a step back and look at the data and then maybe reassess the core processing and sampling plans, because we don't have a lot of material to go around. So we have to make sure that our sampling plan is really meeting all our scientific goals. When we are back in Bremen, we work on the split section and the discrete samples. So again, we work for the legacy data set with the discrete samples on moisture and density and P-wave velocity. The split cores get the digital line scan, XRF, and color reflectance done on them. Before the science party arrives, we conduct thermal conductivity measurements because they're just very time consuming. So it is also great when they're done before everyone arrives. And if the science calls for it, we can also integrate geotechnical measurements into the workflow during the onshore science party. But before we go to an onshore science party, we go back offshore, and I will ask Erwan to take over here and talk to us a little bit more about downhole logging.
Hello, everyone. Are we good? I hope you can hear me and see me.
All good.
Yeah,
good.
all good, Erwan, yeah.
Cool. You know, after 1 year, it's still a classic. I have to check. You know, never know. So following physical properties measurements on the cores. Let's look at downhole logging. And obviously, it's 10 minutes presentation, so I won't have time to go into details of every measurement. So we will just scratch the surface to understand what is downhole logging and why it's important to take the time to collect this kind of data. Right, back to this slide with the different scales. So Katharina was talking about physical properties we measure on the cores. And at the very beginning of your idea of a drilling, you were probably looking at larger scale features such as seismic scale, so more toward the right of this illustration. And the downhole logging, first of all, is a link between the cores and larger scale, so it's quite an important measurement to take. It's a real connection. And if you look at your proposal, when you write it, there is a section about operations. And in this section about operation, there is a table about a logging plan. And you have two main options, one being wireline logging and the other one being logging while drilling. So logging while drilling is a bit more exotic because when you do that, you don't get any cores. So I won't focus on that. I will focus on wireline logging, which is the most common form of logging within IODP. And usually then you will be selecting wireline logging, and then you have a selection of tools and measurements to select. The only thing I can say without going into much detail about all the measurements is that ESO doesn't really run radioactive tools. So it means we don't run tools for the measurements of density, for example. So that's something to consider. And when you write your proposal, you have to give an estimation of the time it will take for the drilling as well as the coring. So here, for example, typically a logging session will take 2 to 3 days. So you have to take in account that, the collection of logging data downhole will take up to 10 to 50% of your time at sea. So that's non-negligible, but it's worth it. So it means when you do that, you don't get any cores, but you get in situ data, and I will come back to that later. So what is downhole logging? So it's the collection of in situ and continuous data. Like for physical properties on the core, we will collect very similar data, including the formation resistivity, gamma ray, magnetic susceptibility, acoustic velocities in the formation, and we can also have images downhole. So on the left picture here, you have a logging engineer looking at real-time data during logging operation. The computer is connected to some acquisition equipment, itself connected to a winch, and this winch will deliver some cable, and the cable is connected to a tool, and we send this kind of tool downhole once we've completed drilling and coring operation. So traditionally, we use tool strings, so we combine tools to save time. Instead of sending one tool after the other, we can combine 3 to 4 of them to save time, basically. So to continue with what is downhole logging, this is a very simple illustration with a drill ship, and the 2 black lines represent the drill string. So we've completed coring and coring operation, and we reached the target depth, let's say. And at this stage, we decide to bring the drill string up. And then depending on the quality of the hole and the formation, it can be done in multiple stages, but in a perfect world, let's say, we can bring the drill string up, still connected to the seafloor, obviously, to guide the tool from the boat to the borehole. And we will focus on preferably collect data in this open hole, so we have direct measurement of the formation in situ. And what happens is we send the tool down in the drill string. It will go all the way down the hole and then up again, and we measure data on the way down as well as up. And most of the data we keep are from the way up for accuracy reason. And then at the end of logging operation, you have a data set which is a variable, be resistivity or sonic versus depth. So that's what downhole logging is. And why is it so important? Well, first of all, it's continuous data. If you look at your cores, that's what you get on the boat. The recovery might not be perfect. You know, as we've seen from previous presentation, it can go from, I don't know, 50 to 100%. So you're not sure to get all the information you were aiming to, and you will be missing data. So the core data you will measure will have some gaps. And with logging data downhole, you will have a continuous data set. So it will help you to have a more complete data set, let's say. And also it's in situ data. So even if the core recovery is good, maybe the core quality is not always the best. So for example, on the left picture, on the left here, you have biscuiting. So you have like this backbone structure because the formation has been broken into small bits, and on the side it's been completely washed and redeposited within the core. So you don't really know if what you're looking at is the actual formation. And you can also drill and core brecciated and fractured zones, and maybe the drilling and the coring itself will damage the formation even more. So are you sure your cores represent what's going on downhole? So that's why downhole logging is so important, because you see what's happening in the formation in the hole. An example about core recovery. So let's say you've been drilling 3 meters and the recovery comes like this. You have bits of formation in your liner and the crosses represents gaps. At the curation, what they will do, and they traditionally do that in IODP, you bring all the bits toward the top of the core and you measure the recovery. So let's say you drill 3 meters, you recover 1.5 meters maybe. So you got 50% recovery, but you don't really know where these bits really sit next to each other in the borehole, or if you've lost some formation during your coring. An example, classic MSP example, is this drilling through some carbonates. And here on the left part, you have 2 sections, let's say, and you have a gap in between them, meaning, you know, probably missing some rocks. But if you look at images downhole, you can see that you have at least 2 natural gaps in the formation. So based on that, it's possible to replace the bits where they really belong to and realize you are not missing anything. There is just nothing to drill. That's why you have a gap. So that's one of the use of in situ data. Other very powerful use of in situ data is the use of images again. And I'm showing images here, but I could show you wiggles as well. But I think images will talk more. You can pick the structures you see in the borehole. They can be fractures, cracks, beddings, and you can orientate them to the magnetic north, meaning you can understand the structural geology and sedimentology within the borehole. And you can also reorientate the cores based on these data sets. Just a quick note about the tools and their size. So some of you might be familiar with the geodash resolution or the GQ. So it's just to show the scale of these tools. So on the GQ, when they do, for example, logging while drilling, the tools are quite large, up to 20 centimeters in diameter. On the geodash resolution, wireline logging tools are 8.5 centimeter diameter, roughly. And the tools we use within ESO, traditionally, because we have them, are much smaller in size, in diameter and in length. You can see on the side here. We can use other tools if necessary, but that's what we use because we have them, you know, at all time. And differences in tools between different platforms will come with benefits and limitations. So that's one of the reasons you might want to contact ESO when you write your proposal to know what's the best option for you. Quick notes about the data. So I think the logging data are the only one that are not hosted by an ECORD website. So all the IODP MSP data from ECORD and ESO are hosted on a Maroon website or Pangea website. The logging data, ESO send them to Lamont and they are collected with all the IODP data there. And if you are curious about the data generated during an expedition, downhole logging data, you can go and look at expedition or different tools and look at what you can get. They come in raw data, process data. So if you are curious about it, you should consult this website. And just to finish, so physical properties on cores, but also downhole logging, they are quite relevant to the lithology, the sedimentology, the formation fluid, physical properties, and eventually rock mechanics and more. The possibilities are quite large. And these measurements, they also can be integrated, if you look at the bigger picture, to wider problematics such as paleoclimates, correlation between different holes, between the hole and the seismic. You can also do structural geology, hydrogeology, and more. So that's the range of stuff you can do with downhole logging. And that's it for me. So I will stop sharing. Thank you.